All right, Unit 11, parametric vector and polar functions. So it's pretty challenging, but it gives you a really big opportunity to get a leg up on the test because a lot of people can't handle the polar coordinates. So at the end of this chapter, you should be able to graph parametric curves. You can already do that. Find the slope and concavity of a parametric curve, no worries. Calculate the arc length of a parametric curve. I think you most all already know how to do that. Work with two-dimensional vectors and vector operations. That's physics stuff. It's not easy, but it's not that hard. Model motion in a plane with a vector and determine velocity, acceleration, and speed. Calculate displacement and distance traveled. A little bit tricky, but not the end of the world. Graph and work with polar coordinates. That's goofy stuff. Once you practice, it's not a big deal. Determine the slopes of polar curves. That's easy. And then find the areas. That's sometimes pure evil, but well, we'll see how you handle it. So, what's a parametric function? Is it always a function? No. Parametric is the function it represents. That's wrong. The model represents maybe. I'll give you an example. So it's a parametric function is something that's defined with another parameter. In this case, t. Why would we use it? We've talked about this before because we don't just want to know the motion of something through a plane. We want to know when that motion happens. So we need x, y for a plane, then we need t for the time. So we have to put it all together. Examples are x equals sine of t, y equals cosine of t, 0 is less than equal to t is less than equal to 2 pi. All right, that's going to be a circle. Is a circle a function? No, it most certainly is not. All right, more on this momentarily. So sketch the following curves, identify those that define y as a function of x. Sure, whatever you say. Find an equation that relates x and y directly. I don't know about the identifying, but let's see what we got here. So plug in 0. Cosine of 0 is 1. Sine of 0 is 0. So it starts there. As it goes around 2 pi, if you try pi over 2, hey, that's at 0. Pi over 2, that's at 1. It starts here. It actually overlaps itself just briefly there at the starting point. But that's okay. So back to the question, hey, is that a function? No, that is not. Is x equals cosine of t and y equals sine of t a function? Yes, it is. It's important because now we can do calculus to them. Oh, let's do all that nonsense our evil junior level teacher made us do. How do we convert this? I don't know. I'll square them both, see what that does. Y squared equals sine squared t. What if I added them together? X squared plus y squared equals sine squared plus cosine squared. Hey, yeah, I know what that equals. That equals 1. Oh, look at that. So how did I know to do that? I don't. I just play with it and I eventually get there. Parametric polar equations are kind of higher level math. There's all this weird stuff that starts happening that people are not used to. So that's one of the tricks. Square them both, see if you can get rid of the parameter. We're going to do it here again, except we have to make a little exception first. Plug in 0, plug in pi, plug in everything. And you will see that you get something that looks like a little football. This is the starting point. And it heads this way. So remember, parametric, it matters where it starts, matters the direction it's going. Because it's parametric, it's more than just, the curves you're used to. So what do? I think I'll divide each one so that I get the cosine and the sine alone. Because I know when I do that, I can square both sides. So we get x squared over 9 equals cosine squared, y squared over 4 equals sine squared. Okay, let's add them down. We'd get x squared over 9 plus y squared over 4 equals sine squared plus cosine squared, also known as 1. Hey, I know what that is. That's an ellipse. I've taken algebra 2. I know what I'm doing. Yay. All right, let's try another one without all the fancy trig. X equals root 2t and y equals t minus 2. I don't know. 0 to 4, plug in 0, I get 0, plug in 4, no, 0. See, that's how it's confusing. I get negative 2. Sure, whatever you say. Starts here. Plug in 1, I get square root of 1 is 1. Plug in 1 minus 2, I get negative 1. I'm going to plug in 4. I'm jumping to all the perfect squares. I get 2. And plug in 4 minus 2, I get 2. It looks like a parabola to me. I don't know. To think about this a little bit. And of course, this is our starting point. How do we put those together? Well, x squared would be t, so we square both pieces. For the other piece, y plus 2 would equal t. Well, you just sub in t. X squared equals y plus 2. Y equals x squared minus 2. Hey, that is a parabola. Starting at negative 2, and off you go. Well, that's nice. So, how about calculus? How do you find the slope of a parameterized curve? Now, make sure we are clear about this. They're going to ask for the slope of the curve. And everybody gets lost thinking, well, that's got t's and all this in it. No, when they say find the slope, they're saying, what is dy dx? Well, what's with all the t's then? Well, yeah, okay, we got some work to do, but that's what they're asking for. When they're asking for concavity, they're asking for the second derivative with respect to x. So we got this little trick we do here, which you should have seen before. We're going to also do it in polar. Dy over something, dx over the same thing, cancel, we're left with dy dx. This is brutal. How about the second derivative? What's y prime? Y prime, as I just said, is dy dx. So you take this first derivative, you take the second derivative of that whole thing with respect to t, and then you just divide by dx dt again. This bothers me. It's challenging. It makes me think too hard. I don't like it. So concavity is just, again, what's your second derivative? That's it. So here we go. We'll knock it out. Consider the curve defined parametrically by all this nonsense. I'm going to graph it. 0 to 5. I'm not going to be very clear about it. It's something like this. Starts here. Think, plug in 0, negative 5, plug in 0, 0. Yeah, sure. Goes up here. Plug in 5. And then it gets really big. 25 minus 5 is 20. And that's the x value. 5 over here doesn't mean anything. I don't know if that's where it ends. That's just basically what it looks like. Yes, to help you out. All right, indicate the direction, blah, blah, blah. Find the highest point in the curve. Find the highest point in the curve. We need dy dx. Okay, well, dy dt is 2 cosine of t. And I got to be careful here. I got to find where the 0 is on that. 2 cosine of t equals 0. Cosine of t equals 0. T equals pi over 2. I don't think I'm going to need that, but I'm just being aware in case something goofy happens later. Dx dt equals 2t. Well, that one's easy. That's when t equals 0. Sure, whatever. All right. Now what? Oh, Yeah, so dy dx equals dy dt, 2 cosine of t over 2t. When does that equal 0? Well, we already did that. That's at t equals pi over 2. And the bottom is not 0, so we don't have a 0 over 0 thing. So t equals pi over 2. Okay, sure. So where's the point? The point is when x equals pi over 2 squared minus 5, negative 2.533. And when y equals the original y, 2 sine of pi over 2, which is 2. So this peak up here looks like it's over here somewhere, right? That's where the derivative equals 0. And apparently this point is negative 2.533 comma 2. That is where the max happens. How do I know? Well, I'd have to plug this in and see it's negative 4. Well, that's why I graphed it, so I don't have to do all that nonsense. Cool. Hey, that was a piece of cake. Oh, wait a minute. What about points of inflection? Yeah, oh lordy. Okay, so you take the derivative of this. That's what I set up here. Derivative of dy dx, d dy dx. Oh lordy, chain rule will take forever. No, it's not too bad. So dy dx equals cosine of t over t. D squared y dt squared is low d high so low d high, sorry, got interrupted there for a brief moment, sine of t minus high cosine of t d low 1 all over low squared t squared. Could do some simplification. I don't know if I will. So d squared y dx squared. Confused yet? Yeah, look at that. dt squared dx squared. Wow, that's just nasty. Is that over my original dx dt, which was just a t. So what do we got here? I'm going to factor out the negative. You know why? Just because. Sine of t plus cosine of t over t to the third. No, over t squared over dx dt. Where'd dx dt go? Don't forget the 2. 2t equals negative, find all points of inflection on the curve, negative t sine of t plus cosine of t over 2t to the third. All right, set the top equal to 0. Found out that it's when t equals 0.798, because there's no way I can do that. I had to use my computer. And then that's at an xy of 2.831, comma 0.673. It looks like there's a point of inflection over here somewhere where it's starting to bend down, and I guess I drew this wrong. It's starting to curve up from here over. What a mess. But yeah, that's why I call it tricky. What else? Well, we can find arc length. Yeah, I already showed everybody how to do this. Remember, for regular equation, it was 1 plus dy dx squared. Here, it's just that. So let's just find the length of an asteroid. Oh, what? Troid? It's an asteroid. Asteroid? Did you misspell it? Nope, it's called an asteroid. I know you all want to criticize. It looks something like this. Something like that. Pretty cool stuff. 0, you get your 1, 0, so that's the start point, and then pi over 2 gets you to here, I'm guessing. So I think I can just do it from 0 to pi over 2 multiplied by 4, because it is symmetric. Yeah, let's do that. All right, so dx dt is 3 cosine squared t sine of t. dy dt, 3 sine squared t cosine of t, negative. I think. Yeah. Okay. Gotta square it. So the negative didn't matter. 9 cosine of the fourth t sine squared t. Square it. Alrighty. The length is 4 times because we just did 1 from 0 to pi over 2. Square root of 9 cosine to the fourth t sine squared t plus 9 sine to the fourth t cosine squared t dt. Holy heck. Now, hang on a minute. Pull out the 9, doesn't become a 9. Factor out 9 and square root it, we get 12. I can take out cosine squared and make it cosine. Now I gotta think about this for a second. Yeah, I took that out. Let's see what happens with everything left inside. My notes are telling me something here, but I'm not necessarily believing it. Cosine squared t, sine squared t. So I can take that out. Left with just cosine squared t plus just sine squared t. Well, how nice is that? 1. I can take the square root of those. Cool. Well, I got a whole absolute value thing going on here. Yeah, because, you know, square root of a square. Got to be careful. I'm going to ignore that just because I'm lazy. Sorry, I nearly forgot about y'all. Pi over 2 sine cosine dt. Again, should be absolute value, whatever. Now, you could actually do this either way. I'm going to assume it's sine. 12 sine squared t over sine, over 2. 0 to pi over 2. See how I did? 2 sine cancels 2 sine of t. Hey, it looks like I got it right. Equals 6, 12 over 2. All right, I have a little confusion here. No, I'm good. Sine of pi over 2 is 1. Sine of 0 is 0. 6. How crazy is that? Exact distance of this is 6, 3 halves, 3 halves, 3 halves, 3 halves. Adds all up to 6. Cool math. Yep, that's it. Good luck.